So our project was this autonomous Rover. There's two driving modes. We have manual, where forward is right trigger, backward is left trigger, turning is right joystick, and you can move the camera with the D-pad. We also have a spin mode. Left bumper spins around. So yeah, we also have turbo mode, where if you enable it, it can drive twice as fast. So the goal of this project is to autonomously track and locate objects given a color set by the Xbox controller. So you can choose red, green, blue, or yellow, and the camera will track the object.
So from a hardware point of view, Valator has 4 motors to move around on. Each motor has a encoder connected to it, so we can retrieve the current velocities. Along with the encoders, each motor has an H bridge, which we send the PWM signal to control the motors. For our servos, we have 2 servos to control the camera angle. We have panning servos as well as tilting. And for power regulation, everything runs on a 12-volt battery. We have voltage converters or 5-volt regulators for the servos and encoders, and we also have voltage monitors to monitor all these voltages. Some future expansions we had. We have a gyroscope on here as well as a battery gauge. Unfortunately, we did not have enough time to implement these, but given more time, we would obviously do that. And that wraps up for hardware.
Software infrastructure, we utilize Robot Operating System to manage all of our separate processes and communication between our separate processes. At the heart of it, we have our motor API that takes commands in from our user input ROS node and our autonomous navigation ROS node and converts those commands down to lower level motor control commands and servo commands. So we have 4 ROS nodes that are doing DC motor control. Each one of those nodes is running a PI control loop with feedback from the optical encoders on each motor to give us a constant velocity. And we also have 2 servo controllers so that we can move the web camera. Additionally, for our autonomous navigation mode, the user can enter that mode through the Xbox controller, at which point the nodes switch control to autonomous navigation, and then we can do our color targeting.
So here we are in autonomous mode. What's going on here is the web camera grabs a new frame, segments out the colored pixels that we have targeted. So in this case, we're looking for green pixels. Then forms a bounding box around the target object and computes the error between that target bounding box and some defined bounding box that we have in our software. So those 2 errors between the X and Y error and the area error get fed into PID loops, which just try to minimize the error, driving the rover towards the object until there is 0 error. So we utilized OpenCV for this portion of the project. Really the main challenge here is the frame rate. As the rover drives closer to the object, it's not able to pick up the fact that it's moved too close, and then it in turn drives backwards and gets sort of in a looping motion where the frame rate just never catches up to tracking the object. But for the most part, it works pretty well, tracking it left and right, forward, backward. It just sort of struggles with the frame rate in that.
So now we're going to talk about some of the major milestones from the project, kind of working from the bottom up. The very first one was actual construction of the robot, which was constructing the actual body and putting the wheels onto it. Then moving on from there, we were able to work on the PCB design and actual testing of it once we got it back from the manufacturer. And all of this was kind of like happening in parallel as well. So while that was going on, we were also working on kind of the motor control, controlling the actual motors that will drive the robot. And also then, in parallel with that, was kind of ROS integration between the separate nodes that we talked of earlier, where the motor API and the higher level nodes will be able to speak then with the bottom ones and kind of send out those commands to the motors. And once we had the manual driving implemented after everything had been tested, we then moved into actual autonomous navigation, which would take the input from the controller and kind of work hand in hand to kind of control how the motor API was going to work in order to send out the desired velocities to the motors. And we ran into some hang-ups with setting up the PID loops and getting the K values correct. And that was probably one of the biggest challenges that we had kind of moving forward and getting everything tested and ready to go. And moving into kind of how we managed all of this and kind of overcame some of these challenges, it was probably number one, the most helpful thing was using Git for source control. So anytime if we had implemented a new feature and it did not work correctly, we could very quickly revert back the changes, which we did have to do a number of times, and even the night before actually getting ready for the presentation, which kind of caused some panic maybe temporarily, but Git helped kind of offset that. Next was using Slack, which is a messaging tool that's becoming pretty popular in the industry to kind of communicate our ideas and connect in any information that we need right into the messaging app. And finally, we had daily meetings. We were fortunate enough that we are good friends and roommates coming into this project, so we were meeting basically every day and kind of throwing ideas off of each other. But I think with any team, even if you're not doing that, it's important to have weekly meetings and maybe even meet a little more frequently than that. So I think all these things combined kind of produced the final product and really made this semester successful.